Okay. Today's lecture, solution of partial differential equations. So in the last lecture, we explained formation of partial differential equation by two methods. By method of elimination of arbitrary constants, by method of elimination of arbitrary functions. Through this lecture, we are going to discuss the solution of partial differential equations, particularly by direct integration. So before explaining different methods of solving partial differential equations, I would like to explain some definitions regarding solution of partial differential equation. So the first one is the complete integral. I already mentioned that a solution of a partial differential equation is the value of the dependent variable which satisfies the equation. In the case of ordinary differential equation, solution of a ordinary differential equation represents a system of symmetric curves, a system of curves. Whereas in the solution of a partial differential equation, geometrically that represents a system of surfaces. Okay. So anyway, first we go through the term complete integral. So what do you mean by complete integral? Any equation f of x, y, z, a, b equal to 0 involving two arbitrary constants and satisfying the first order partial differential equation capital F of x, y, z, p, q equal to 0 is called the complete integral of the partial differential equation. It is also called the complete solution of the partial differential equation. So that is an equation which is a solution of the given partial differential equation which contain the same number of arbitrary constants as the number of independent variables. That is, the first order equation contains two independent variables. Its complete solution contains two arbitrary constants. So the number of arbitrary constants in the solution is equal to number of independent variables in the first order partial differential equation. So that is the idea of complete integral. Another term is particular integral. That is same as in the case of ordinary differential equation. Particular integral of a partial differential equation, capital F of x, y, z, p, q equal to 0 is the solution obtained by giving particular values to the arbitrary constants a and b in the complete integral. We are assigning particular values for the arbitrary constants in the complete integral. You will get the particular integral. Okay. Now the next term, the general integral or the general solution. So the definition is this: a solution of a partial differential equation containing an arbitrary function is called a general integral. This is the case of a first order equation. In a general case, the number of arbitrary functions in the general solution of a linear partial differential equation is the order of the partial differential equation. That is, in the case of a linear first order partial differential equation, general solution contains one arbitrary function. In the case of a second order partial differential equation, number of arbitrary functions is 2 in the general solution. Okay, so the number of arbitrary functions is equal to the order of the partial differential equation. So the general solution of a linear partial differential equation pp plus qq equal to r is given by phi of uv equal to 0, where phi is an arbitrary function. Now another term is singular integral. Singular integral is the envelope of family of surfaces f of x, y, z, a, b equal to 0, parameters a and b, if it exists. So it is the envelope of family of surfaces. Envelope means it is a surface tangential to all system of surfaces, all set of surfaces, the family of surfaces. Okay, so that is referred as a singular integral. So these are the four terms relating to the solution of partial differential equation. Anyway, initially we will discuss solution of partial differential equation by direct integration. So the basic principle of finding solution of a differential equation is the method of integration. Okay, so initially we will discuss if we have the partial differential equation where we apply direct integration to get the value of the dependent variable. Actually, that is possible when the dependent variable is explicitly expressed in terms of the variable or its in its derivative, like this. Anyway, I will explain the method with a problem. Okay. Problem 1. Solve the partial differential equation dou square u by dou x square equal to 12x square into t plus 1, given that u of 0 t equal to cos 2t and dou u by dou x at x equal to 0 equal to sin t. These are called some conditions, initial and boundary conditions. Okay. So this is a initial value problem. So partial differential equation, some boundary conditions are referred as a boundary value problem. Having some initial condition is referred as an initial value problem. Okay. Anyway, we have this equation. How we solve this by direct integration. So in order to solve this partial differential equation, we have to apply integration successively. Okay. So look at this partial differential equation. Dou square u by dou x square equal to 12x square into t plus 1. So here u is a function of x and t. So we integrate this given partial differential equation with respect to x, keeping t as a constant. Here u is a function of t, x and t. So integrating this dou square u by dou x square with respect to x, keeping t as a constant. So what is the result? Dou u by dou x equal to here 12 into t plus 1, that is the constant. So we take initially 12 into t plus 1 into integral of x square, that is x square by 3, plus constant of integration. As we treat t as a constant, that constant may contain functions of t. So I write the constant of integration as c1 of t because we are treating t as a constant. Okay. Now we have this equation. Now integrating this equation 2 again with respect to x, keeping t as a constant. So you get u of xt, integral of dou u by dou x with respect to x is u of xt. And here again we have 12 into t plus 1 into x cube by 3, that is to be integrated, and 12 by 3 is 4. So 4 into t plus 1. Integral of x cube is x raised to 4 by 4. Plus integral of c1t is c1t into x, because we are treating c1t as a constant. Plus another constant of integration, that is c2 of t. We take the constant of integration as a function of t because we are treating t as a constant. Okay. Now this equation can be reduced to this format: t plus 1 into x raised to 4 plus c1t into x plus c2t. That is equation 3. So this is the expression for u of xt. Actually, this is a solution. If you have no boundary condition, this step completes the solution of the problem. But here we may have some boundary conditions. We have some boundary conditions. U of 0t equal to cos 2t and dou u by dou x at x equal to 0 equal to sin t. These boundary conditions are generally used to determine the arbitrary constants or arbitrary functions involved in the general solution. And here c1 of t and c2 of t are the functions of t. So we have to determine these c1 and c2 by applying the boundary conditions. So initially we apply the first boundary condition, that is u of 0t equal to cos 2t. That is value of u at x equal to 0 is cos 2t. That is the first condition. So I am applying the boundary condition on equation 3. This is our expression for u of xt. So I am applying the boundary condition 1 on this equation. So what is the left side? U of 0t, that is cos t, what is given. So cos 2t, that is equal to, on the right side, when we put x equal to 0, the first two terms get cancelled. Because x equal to 0, these two to get cancelled. So we have the third term, c2t. So what we get is cos 2t into c2t. That will give the value of c2t. I am substituting the value of c2t on this u of xt. That is equation 3. What do you get? U of xt equal to this one. T plus 1 into x raised to 4 plus c1 of t into x plus c2 of t is cos 2t. So plus cos 2t. We have the equation 4. Now we have one more boundary condition, that is dou u by dou x at x equal to 0 is sin t. And for applying this, we have to find dou u by dou x. Okay, dou u by dou x. And this is our expression for u of xt after applying the first boundary condition. Then I am differentiating this fourth equation partially with respect to x. That is taking t as a constant. So on differentiating the first term, that is t plus 1 into x raised to 4, we get t plus 1 into 4x cube. That is 4 into t plus 1 x cube. Second term, we are differentiating with respect to x. So the derivative of the second term is c1 of t. Third term is completely a function of t. So on differentiating with respect to x, as it is independent of x, cos 2t is independent of x, the corresponding term is 0. So what we get is dou u by dou x is 4 into t plus 1 into x cube plus c1 of t. Okay, so this is dou u by dou x. Now I apply the second boundary condition, dou u by dou x at x equal to 0 equal to sin t. So the left side is sin t. On the right side, we are putting x equal to 0. So this term get cancelled. You get c1t. So c1t equal to sin t. Substituting the value of c1t in this equation, the fourth one, we get u of xt equal to t plus 1 x raised to 4 plus c1t is x. C1t is sin t. So what we get is x sin t plus cos 2t. Now this equation independent of arbitrary functions. So this is the solution of the given partial differential equation. So this is a method of solving a partial differential equation by direct integration. Okay, so that's a procedure. Now we look at another problem where we can apply the same method to solve the partial differential equation. Solve the partial differential equation dou square u by dou x dou y equal to sine of x plus y. Given that dou u by dou x at y equal to 0 is 1 and u of 0 of y equal to y minus 1 the whole square. These are the conditions, boundary conditions. Okay. Now, so the equation we have is dou square u by dou x dou y equal to sine of x plus y. Our aim is to, and our objective is to find u. Okay. So what we do is integrating with respect to y. We may start with x or y. I am here. I am starting with y. Integrating with respect to y, keeping x as a constant. Okay. So what you get on the left side, dou u by dou x. And the sine of xy, I am integrating with respect to y. So we get cos of x plus y plus c1 of x, because I am treating x as a constant. Applying the boundary condition dou u by dou x at y equal to 0 equal to 1, because this expression of dou u by dou x, and applying the first boundary condition on this equation. Integral of sine of x plus y is not plus cos of x plus y, it is minus cos of x plus y. Okay, that is why minus cos of x plus y plus c1 of x. Applying the boundary condition dou u by dou x at y equal to 0 equal to 1, but we get 1 equal to minus cos of y is 0, so cos x plus c1 of x. We get this, which implies that c1 of x equal to 1 plus cos x. So we get the value of c1 of x as 1 plus cos x after applying the first boundary condition. So what is dou u by dou x? Minus cos of x plus y plus 1 plus cos x. Is it clear? So that is dou u by dou x. Now our aim is to find u. So we have to integrate again this dou u by dou x with respect to x. So now integrating with respect to x, keeping y as a constant. So on the left side, we get u of xy. Okay. On the right side, integral of minus cos of x plus y with respect to x. That is minus sine of x plus y. Then integral of 1 with respect to x is x. Integral of cos x with respect to x is sine x. So we have up to this. That is the integral of these two terms. Okay. Plus constant, as we keep y as a constant, we may write constant as c2 of y. Is it clear? So that is expression for u of xy. Now we have one more boundary condition, that is u of 0y equal to y minus 1 the whole square. We apply this boundary condition on this equation. That is putting x equal to 0, the value of u equal to y minus 1 the whole square. So on the left side, we have y minus 1 the whole square. On the right side, we have to put x equal to 0. So minus sine y, that is the first term. Second term, 0. Third term, sine x sine 0. Then c2 of y. So what left on the right side is minus sine y plus c2y, which implies that c2y equal to y minus 1 the whole square plus sine y. Okay, so that is c2y. Substituting the value of c2y in equation 1, but we get u of xy equal to minus sine of x plus y plus x plus sine x c2y equal to sine y plus y minus 1 the whole square. So that will give the value of u of xy. So this is the answer which gives the solution of this partial differential equation. Okay, it's problem 2. Now we take another problem. This is a third order equation, but having no boundary condition. Okay, so solve the partial differential equation. Dou cube is set by dou x square dou y plus 18xy square plus sine of 2x minus y equal to 0 by direct integration. So here again we have one term of partial derivative, which is a third order partial derivative. So we have to integrate twice x, then once y. Anyway, we're starting with integrating with respect to x. First, we integrate with respect to x, keeping y as a constant. So this is a step. Dou cube is set by dou x square dou y. While we integrating with respect to x, when x is cancelled, we get dou square is set by dou x dou y. Okay. 18xy square. Integrating with respect to x, what do you get? 18 into x square by 2. That is 9x square y square. Plus sine of 2x minus y. That is minus cos of 2x minus y divided by 2. Okay. Equal to 0. On integration, we get c1 of y. So that's the first step of integration. Integrating again with respect to x, keeping y as a constant. So first step become dou z by dou y. And this become 9 into 2 into x cube by 3. So 9 into 2 into x cube by 3. Sorry, integration 9 into x cube by 3. So 3 get cancelled. So 3x cube into y square. Okay, integral of 9x square y square is 3x cube y square. Then integral of this term is minus sign here. Integral of cos of 2x minus y is sine of 2x minus y by 2. So by 4. Already there is a 2, so it's by 4. Equal to x into c1 of y plus c2 of y. Is it clear? So it is again integration with respect to x. We have this term. Now we integrating with respect to y, keeping x as a constant, because we have dou z by dou y and we require z. So integrating with respect to y, keeping x as a constant. So this term on integrating with respect to y, we get z. Then with respect to y, so 3x cube into y cube by 3, 3 get cancelled, we get x cube into y cube. And on this term, minus integral of sine of 2x minus y is minus cos of 2x minus y by minus 1. Okay. So in effect, we have this this minus sign, and integral of sine 2x minus y is minus. So this become plus. Now cos of 2x minus y divided by minus 1. That minus 1 combined with the 4, we get minus 4. Okay. So integral of the left side. On the right side, we are integrating with respect to y, keeping x as a constant. So I take x outside. X into integral of c1y dy plus integral of c2y dy plus constant of integration, that is c3 of x. So that is expression. Okay. On simplifying this, what we get z plus x cube y cube plus cos of 2x minus y by minus 4 equal to x into, I take integral of c1 of y as a function of y and put it as f of y. And second term is another function of y, we put it as g of y. And third is a function of x, we'll write c3 of x. So if we write that as h of x, I'll get the solution like this. That is z equal to, I'm taking all other terms to the right side. So plus x cube y cube become minus x cube y cube, and minus cos of 2x minus y by 4 becomes plus cos of 2x minus y by 4 plus x into f of y plus g of y plus h of x. Okay, so that is the solution of this partial differential equation. So this is the idea of solving a partial differential equation by direct integration. Anyway, one more problem we have, that is solve the partial differential equation. Dou square is set by dou x dou y equal to sin x into sin y. Given that dou z by dou y equal to dou z by dou y at 0 y equal to minus 2 sin y, and z equal to 0, when y is an odd multiple of pi by 2. Okay. So in this problem, we start with the partial differential equation dou square z by dou x dou y equal to sin x into sin y. So to solve this equation, we are integrating with respect to x, keeping y as a constant. So while integrating with respect to x, the integral of this term is dou z by dou y. It is equal to integrating with respect to x, not with respect to y, with respect to x. Okay. So sin y into integral of sin x, that is minus cos x, plus c1 of y. Okay. Applying the boundary condition for dou z by dou y, that is given, it is minus 2 sin y. So when we apply this boundary condition, that is dou z by dou y at 0 y equal to minus 2 sin y, we are applying the boundary condition on this equation, but we get minus 2 sin y equal to, we are putting x equal to 0, so cos 0 is 1. So we get minus sin y plus c1 of y. Therefore, c1 of y equal to, I am taking this minus sin y to this side. So minus 2 sin y plus sin y, that is minus sin y. So we get c1 of y equal to minus sin y. Okay. So dou z by dou y becomes minus sin y cos x minus sin y. So this expression for minus expression for dou z by dou y. Now again integrating with respect to y, keeping x as a constant. So what do we get? Integrating this with respect to y. So we get z. Here we have minus cos x into integral of sin y, that is minus cos y. So what we get is plus cos x into cos y. Then minus sin y. Integral of minus sin y is plus cos y. So we have plus cos y here. Okay. Plus constant of integration, as we treat x as a constant of integration may be written as c1 of x. Okay. So we have z equal to cos x into cos y plus c1 of x. Now applying the second boundary condition, that is, what is the second boundary condition? Z equal to 0 when y is an odd multiple of pi by 2. Okay, y is an odd multiple of pi by 2. So y is an odd multiple of pi by 2 means cos pi by 2, cos 3 pi by 2, cos 5 pi by 2, etc. are 0. So these two terms get cancelled. Both the first two terms 0. So what we get is 0 equal to c1 of x. That is c1 of x equal to 0. Now substituting, we get z equal to cos x cos y plus cos y, which may be written as z equal to 1 plus cos x a whole into cos y. Okay, so that's the general solution of this partial differential equation. Okay, so with this we can stop this lecture.